Thank you. So I'd like to thank all the organizers for the invitation. It's really a pleasure to be here. I'm going to talk about hydrodynamics with spin. This is my perspective on hydrodynamics. This is work that's been done with this group of people. So Casey is a postdoc at Utrecht. Domingo is in Mexico. Umut, I think you know, and Roy is a student at the Technion. And what I like to do is go over, mostly review, but also give some new results about our perspective on what hydrodynamics with spin looks like and what it means. But before that, I'd like to just explain what I mean by hydrodynamics. So this is kind of a mixed community. For some people, hydrodynamics means kinetic theory. For some people, hydrodynamics means black holes. I want to first sort of give an overview about what I want to refer to as hydrodynamics. Okay, so I'm going to start with something simple that you're all familiar with, just regular hydrodynamics. I have an energy momentum tensor and a current. And in hydrodynamics, the way I see it, we start with conservation equations. And what we want to do is we want to find out some effective theory that will allow us to solve these conservation equations in a state which is close to thermal. And the way we do that, we assume that the stress tensor and the current are specified by a handful of what we call hydrodynamic degrees of freedom. So the number of degrees of freedom should match the number of equations. So we have here a 4 velocity which squares to 1. So this is 3 degrees of freedom, 4, 5, and we have 5 equations in 3 + 1 dimensions. And that's what we want to solve for. In addition, we could have some background fields. Here I wrote the metric and the gauge field. And what we want to do is to determine the most general constitutive relations possible. Okay, that's what I want to call hydrodynamics. I want to figure out what the equations of motion look like. I don't want to compute explicitly what the energy densities or the shear viscosity is. I just want to figure out what is the structure of the constitutive relations. And then for a particular theory, you could use your favorite method to evaluate the equation of state or the bulk viscosity. So how do we determine this? First thing, we use what's called a derivative expansion, which I'll go over. It means that we write the constitutive relations as a series expansion in derivatives. Once we do that, we write down all possible terms that are compatible with the symmetries, and then we use the second law of thermodynamics. So once the equations of motion are satisfied, we expect entropy to increase, and we have to implement, and that turns out to constrain the possible constitutive relations. So what I'm going to do now is go over these steps. There are a few very important features of using the derivative expansion that are often overlooked, and they lead to a lot of confusion later on. So I just want to make sure we're all on the same page. And at the end of the day, what we get is these constitutive relations. And now we can compute the charge density or the conductivity or whatever parameter we want. So let me start with a derivative expansion. By derivative expansion, what I mean is that the stress tensor and the current have to be expanded in derivatives. That means that we have a 0 order term which has no explicit gradients in it, and we have a 1st order term which has explicit gradients in it, and we can go to as high order in derivative as we wish in principle and see what the constitutive relations look like, again, in this type of expansion. Let me put a little epsilon here just to emphasize which order in derivatives we're working in. Yeah. Space-time. Yes. Okay. Space and time. Yes. Sorry. Yes. Okay, so once the constitutive relations are expanded in derivatives, it means that the equations of motion are also perturbative. Okay, if we insist on working in a perturbative expansion for the constitutive relations, it means that the equations of motion should also be treated as perturbative. Okay, now this is a little tricky, so I just want to emphasize this point. So let's look at a harmonic oscillator which is perturbed by an x to the 3 term. Okay, and let's assume that this perturbation is small and there may be higher order terms in this expansion. If we want to solve this, what we need to do is expand the solution in a perturbative series as well. Okay, otherwise, we're not going to get the right answer, or we might get an answer which is not actually valid, or valid only in a certain domain or with a small error. Okay, and once we do that, then we just plug this into the equation and we solve things perturbatively. Okay, so we have the zero order equation where there's no perturbation, and then we have the first order equation which looks like the zero ordered one plus a source which comes from the zeroth order equation. Okay, so this is how we solve an equation of motion that's defined perturbatively. Okay, so strictly speaking, what we need to do if we want to stick with the derivative expansion is we need to expand also our hydrodynamic variables in a perturbative series and solve order by order in epsilon. This isn't what we do, but if we're constructing something in a derivative expansion, this is what we should do, and I'll comment on this later. So for now, as we derive the constitutive relations, we're going to assume that we're working in a perturbative expansion, and that means that we should also expand the hydrodynamic variables in a derivative expansion as well in order to solve them. Okay, next thing we do is to write down all the terms that are compatible with the symmetries. So here are all the terms that I can write down that have zero derivatives in them. And now we can figure out what the stress tensor and current are. It's just going to be some function of the scalars and times a structure which is either a symmetric tensor or a vector. These are the only possible terms we can write down. Often we replace the metric with a projection in the velocity direction. So I'm going to replace the metric here with a projection. And then we can interpret by comparing to thermodynamic equilibrium, we can interpret A, B, and C as energy density, pressure, and charge density. I'm in flat space at this point, but it's not going to be crucial here. Yeah, so I'm assuming that if I have curved space, then I treat the metric as zero order in derivatives so that it's not going to make a difference. Okay, so now we can go to first order in derivatives. So at first order in derivatives, there are three scalars, 4 vectors, and 1 tensor. And here I'm assuming that you can have more things if you break parity. And I'm assuming that the electric field is first order in derivatives. You can fiddle around with that and things get a little more complicated. Okay, and now if I want to write, and now I'm gonna replace gradient of chemical potential with this ratio just because it's going to be more convenient later. And now we can write down the constitutive relations for, say, the current at first order in derivatives. So at first order in derivatives, we take the scalar and we attach it to the only vector we have at zero order in derivatives, which is the velocity. And this is a function of the temperature and chemical potential. So the first scalar here is going to contribute to, this is its contribution to the first order in derivative terms in the current. And then we have the second scalar and the third scalar, and then we start adding the vectors. So in principle, we have 7 possible terms in the constitutive relations for the current. Yes, so that's gonna come in right now. Okay, now the point is that, like you said, I need to really think of the velocity as something that's perturbative. So that means that not all the 3 terms in all the 3 scalars are independent, because once I look at the zero order equation of motion, the zero order equation of motion, which is this, it just tells me that the 3 scalars are not independent of each other. And again, this is because we're working perturbatively in a derivative expansion. So these 3 terms are not independent. And therefore, if I'm working perturbatively, I can relate one to the other two. Okay, so that means I can remove one of the scalars. Yes, but at first order in derivatives, I need to expand, because I'm working perturbatively, then I need to think of the velocity as something that's also perturbative. And then at first order, I always have a zero order term that I want to include. You're right that if I want to work off shell, then it's a completely different story. Okay. Okay, and there's also the equations of motion for the stress tensor and the stress tensor, which I can decompose into a vector equation and a scalar equation. So because I have two scalar equations, I'm going to have only one independent scalar under the equations of motion, and I can lose one vector. Okay, so out of the 7 terms, we're down to 4. And now we can further simplify things by doing a field redefinition. So this is a little bit, again, confusing if you don't think about this in terms of a derivative expansion. So let me just explain what I mean here by a field redefinition. And let's go back to this example of the perturbed harmonic oscillator. So this is a perturbed harmonic oscillator, and we want to solve it perturbatively to linear order in epsilon. And suppose we want to compute the energy of this harmonic oscillator. So here's the energy. What we need to do is to insert the solution into the expression for the energy, expand to linear order in epsilon, and that'll give us the energy for a particular solution. Now, nobody prevents me from just redefining x to some other variable y. I can always do this. Physics is not going to change under whatever choice of variables I make. Okay, so now the equation for y is going to look a little bit different from the equation for x because we tuned it so that it'll look different. We can expand y in a perturbative series, and we get the leading order term and the subleading order term. The equations look very, very different. And at the end of the day, we can compute the energy. And of course, if we put in the same initial conditions, the energy is going to look the same. The only thing we did is just mix our variables. You had a question? The equations will change if you stop treating them in a perturbative expansion. Because you're treating the equations perturbatively, you can add a 3 derivative term. You can redefine y to be epsilon y with 3 derivatives. And what's going to change is the structure of the equation is going to look different, but you have to treat it perturbatively. So when you treat it perturbatively, the only you're going to get the leading order term is going to look like the homogeneous equation, and whatever higher derivative terms you have here are going to be sources. So you can have 15 derivatives here. It's not going to change the structure of the equation because you're solving for y1. Okay, so if you had 15 derivatives here, it's going to track to some 15 or I don't know how many derivatives here, maybe more. But you're solving for y1. So this is an inhomogeneous equation, and this is a source for y1. The source is going to have as many derivatives as you want. If you forget that you did things in a derivative expansion, then you're going to run into a whole lot of trouble, right? You're going to change the structure of the equation, you can change the number of derivatives, you can do many things. But this construction is valid in a derivative expansion, and this is why I'm emphasizing that in a derivative expansion, you have to do this. If you do this and all of a sudden forget that you had a derivative expansion, obviously you're going to get the wrong answer. Okay, so physical quantities should be invariant under field redefinition, again, as long as we're consistent in our derivative expansion. Yes. Yes. Let me do it, and I'm going to do it right now. Okay, so now, in principle, we could do a field redefinition. So here is an example. I'm doing a field redefinition of the temperature. I want to change the temperature, so it's the leading order term is the same, and then the subleading order term is going to be some gradient of something. So we can always do this. It's just a redefinition of what we call a dynamical variable. Okay, and now if we look at the zero order term for the current then the zero order term for the current in these redefined variables is going to have the leading contribution and a subleading contribution, which comes with a derivative because we changed the definition of the temperature. Okay, so once we change the definition of the temperature, what we're going to do is this zero order term is going to shift the first order and derivative term by this amount. Okay, and if it shifts by this amount, what we could do is we could just choose our definition of the temperature in such a way that it'll exactly cancel some of the terms that we have in the constitutive relations. Okay, so this is a field redefinition. In hydrodynamics, it's called a fluid frame, Landau frame, Eckhart frame. It's this. Okay, this is what we're doing. Sorry? Yeah, so you're out of equilibrium. So you want the zero order and derivative term to be the temperature. And then the question is, how do you define temperature when you're out of equilibrium? And you have some freedom in defining it. Because how do you measure temperature out of equilibrium? You cannot. So you can do whatever you want. All you need is that in equilibrium, you have a quantity that in equilibrium reduces the temperature. Out of equilibrium, it does whatever it wants. You can't measure temperature out of equilibrium. You can measure the stress tensor, and that's something that's invariant. That depends what, I mean, you can stick a thermometer in there, and you can say, this is my definition of a temperature. You could do that. But that's going to be a specific choice of frame. Because nobody said that this is, you know, a proper definition of temperature. You could measure, you could, so there's a nice, if you look, there's a nice paper by Pavel where he has two different definitions of temperature, and you can show that, you know, depending on how you measure things, it's just going to correspond to different frames. So what does it mean, a thermometer? It means that your particles are hitting this, you know, hitting your mercury. Well, but now you have to explain what, you know, you can, but this is a device. How do you make that device work? You need an, no, but again, this, so you have a notion of temperature where you want to define it in a particular way in some construction that you call local thermodynamic equilibrium, and that corresponds to a particular frame. It's called a hydrostatic frame. That's a frame. If I want, I can shift the temperature around and it'll change. So if you're saying, I want to measure the temperature in a particular way, then you could do that and you'll get the temperature that you measured. Okay, but velocity, for example, is the same thing. Velocity of what? Of energy, of charge, what's moving? So it's the same, it's the exact same problem. Then there are some privilege, I would say. From a mathematical point of view. So I think you can define. So if you, for example, if you use Landau frame, and you go to second order and derivatives, that will not coincide with what you call local thermodynamic equilibrium. So my goal here is not to define temperature, but to write down the constitutive relations. So what I can do is use a particular fluid frame. You want to change it, you're free to change it, and you can change it to be whatever you want, and there's not going to be any mismatch. There is a frame which allows, you know, to define a temperature in an objective way. Okay, from the point of view of thermodynamics, perhaps we can discuss this later. No, but also you can use Landau frame. Say that using this to redefine the temperature is wrong from the point of No, I understand. No, but what you feel is natural, you can, for example, say Landau frame is natural because I just look at the eigenvector of the stress tensor and I want it to be negative. That's what I'm going to call my velocity, and that completely fixes your temperature. So I mean, natural is in the eye of the beholder, I think. You know. The Landau velocity does not correspond to the velocity, the actual velocity in a rotating fluid. But velocity of what? No, but that's exactly the point, right? Yeah. I don't know, clear. I can redefine it. I mean, again, what I'm saying is, you're right. For certain processes and for certain configurations, there is a hydrostatic frame, what I call a hydrostatic frame, and that's gonna be more natural. But you know, somebody else might say, look, this is what I'm working with. I don't really care about that. I want to use Landau frame, so you know, there's nothing wrong with it. And the point is that you can go from one to the other. It's just a choice of variables. That's all you're doing. Yeah, I think so. No, I think it's the same. Yeah, but it doesn't matter. There is some frame. It doesn't matter what we call it. The point is, the expectation value of, so this is, point is, and I'm about to say, I'll say this again, this expectation value of the current or the stress tensor doesn't depend on the frame you're using as long as you're working in a derivative expansion. Okay, so you can use whatever frame you want to define the temperature. The expectation value of the current is not going to change as long as we're working in a derivative expansion, like the energy that we saw before. So let me just emphasize that and then comment again. So again, suppose we're looking at, yeah. Yes. So no, the equation of state stays the same. The equation of state depends on, so suppose you have energy density, which is a function of T, that you define in equilibrium, and now you can, you know, take T to T plus gradient of something, and that means that this is exactly what I was doing here, right? So rho of T, it goes back into rho of T plus some corrections. So those corrections are just going to be shifted up to the next order in derivatives. I mean, yeah, if you're consistently expanding, yeah. So the equilibrium configuration stays the same. And if you want the hydrostatic, if you want the equilibrium configuration in the presence of sources or with some other killing vector to stay the same, that will fix part of this field redefinition. No, I don't know if the expansion converges. I don't know if well, I'm working to this so the expansion doesn't converge. We know that the derivative expansion doesn't converge. No, the usual one doesn't converge. Sorry. So for that, you need to resum it. Let me say that at the end. I'm going to comment on that. Okay. Okay, so again, if we have the current in one fluid frame, we can go to another fluid frame, and for the same reason that I described before, physical observables are not going to change. And again, as long as we work perturbatively, we have this freedom, nothing's going to change. Okay, and last, we need the second law of thermodynamics. I'm not going to use this a lot, but it constrains further the possible constitutive relations. And and this is the final result for the current. Okay, so this is what I advertised earlier. If you follow these steps, this is what you get. This is the constitutive relations in the Landau frame, where it's a particular choice of temperature and velocity field. And like I said, if you want, you can make a redefinition of the velocity. It's going to shuffle around some terms at first order and derivatives. But if you solve things perturbatively, nothing's going to change. Now, the problem with solving things perturbatively is that we're missing a lot of physics. So there's no turbulence, right? Because there's really no viscosity. All the first order terms are perturbatively small. So if we solve things perturbatively, we're not going to see any turbulence. Shock waves are going to be discontinuous. They're not going to be smoothed out by the viscosity. And if you look at, we're not going to have any sound attenuation. We're not going to have any diffusion, right? Because we're all perturbing around an ideal fluid. So if we really want to treat this as a physical theory, what we say is, well, we just declare that the result is valid beyond the derivative expansion, and that's it. And now we use it as a full theory. So we forget that we use the derivative expansion, and we say, well, let's just assume that derivatives are small. If derivatives are small, and we can just forget about all these problems, and things should be consistent. And once you do that, you have turbulence, and you have smoothed out shocks, and you have sound attenuation. But you run into other problems like causality and stability, and all these problems arise because we treat the equations non-perturbatively. Okay, so we gain something, we gain a lot of physics, but we also lose a little bit. And once we declare that the result is valid beyond the derivative expansion, field redefinitions are going to change the physics. Okay, and this is BDNK. This is exactly what's happening. We're treating the theory as exact, and we're doing a field redefinition. So now, because we're treating the theory as exact, field redefinitions and truncations at second order derivatives are not, it's not going to commute. And so if we want to now solve the problem that's been generated by treating the theory as non-perturbative, then we need to do something. We need some other method to make this system of equations work. Okay, so what I'm after, so this is now a choice. I mean, at this point, there's some physical reality that enters, and if we want to solve a particular problem, we have to do something to these equations that have been obtained perturbatively to solve an actual problem. What I want to do is do the same thing for hydrodynamics with spin. Okay, so I want to follow the exact same steps and see what I get for the constitutive relations for hydrodynamics with spin. I'm going to work perturbatively in the derivative expansion. So I'm going to have freedom of changing frames and using the lower order equations of motion for the next one. And of course, at the end of the day, I'm going to get some set of constitutive relations. If you want to use a different frame, you can easily change the frame and get something that's the hydrostatic frame or Landau frame or whatever other frame you want. Okay. So if we add spin, I don't know if I need to really introduce this. What we want to do is add an extra equation for angular momentum conservation. The stress tensor doesn't have to be symmetric. And what we want to do is just apply the same kind of techniques to this set of equations. And there's an S missing in the current. Okay. So this is what we have for hydrodynamics without spin. We have 5 hydrodynamic variables for 5 equations. We want to add the spin current. We want to add constitutive relations for the spin current. So first thing we need to do is add more degrees of freedom so that we have the same number of degrees of freedom as equations. So I'm going to call this the spin chemical potential. I apologize. I know you like calling it spin potential, but I won't remember it. So I'll just say chemical potential. Okay, so we add a spin chemical potential as an extra degree of freedom. And then the constitutive relations for the spin current is going to look like this. The spin current is, so the stress, if we work with Vielbeins, the stress tensor is going to couple to the Vielbein, the spin current to the spin connection, and the current to the gauge field. And so for sources, we're going to use the Vielbein spin connection and gauge field. And now what we need to do is figure out what the constitutive relations look like. Yeah. So if you have fermions, they're going to couple to the spin connection. Yeah. Well, again, it depends. So if you have an independent spin connection, so if the spin connection is independent of the Vielbein, then the difference between the spin connection, so there's the spin connect, so you have the spin, so there's a spin connection which doesn't depend on the Vielbein. But if you have a Vielbein, you can also define another spin connection. You know, I don't remember what it is, but it's something like that. Yeah, I understand. Hold on. Yeah. Okay. So now I have at my disposal two spin connections. The difference between two spin connections is a tensor. This is a tensor. So you can just contract your gluon fields with this thing. Okay. So you have some freedom of adding this tensor. It's like if you have a scalar field, you can look at couplings of this type. Scalar field in a curved background, you can add this type of coupling. So this is the same thing. If you have an independent spin connection, you can do that. So any covariant derivative you have, you can change, but also even if it's not covariant, you can just add this times whatever tensor structure you have that will contract this. Yeah. Well, I mean, once you have an independent, I'm not going to really use it in this talk, but once if this term is not equal to this term, you have torsion. Which is that? Thank you. Yes, but if you have a Vielbein and you have a spin connection, and this difference is not zero, that difference is equal. That's the definition of torsion or contorsion. Okay. So we need to use a derivative expansion. So what we're going to do at first is just do what we did before. We write down all possible terms that don't depend explicitly on derivatives. I'm saying explicitly because this is going to become, we're going to need to change that in a little bit. Okay, so there's no explicit dependence on derivatives. And I'm going to use some traditional formalism where I decompose the tensors into parts that are parallel and orthogonal to the velocity field. So my spin chemical potential is going to have a vector part and the tensor part. Okay. So now we write down all possible terms that are compatible with the symmetries, and we implement the second law of thermodynamics, and what we get is an expression like this for the constitutive relations. So P here is something that I'm going to identify with the pressure. It's constructed of all possible scalars that one can write down that are associated with terms which have zero explicit derivatives in them. This is the charge density. This weird object is associated with the derivative of the pressure with respect to the velocity field. So usually, because the velocity field squares to 1, it won't enter in the pressure. But now, because we have extra stuff with indices, then the velocity will enter into the pressure. And it turns out that the stress tensor is going to take this form. Yeah. Sorry? This is, I just wrote down the most general thing, and I'm giving you the result. If you get something else, it's going to be incompatible with this. Again, assuming zero explicit derivatives. Zero explicit derivatives is important. I didn't finish writing it yet, but you can, if you're asking about the spin current, let me write it down and then, okay. Yeah. Yeah. What am I holding fixed? Yeah, the spin chemical potential, and the chemical potential and temperature. Yep. Yep. I think that I never thought of it that way, but I think that's right. Yeah. Okay, and this you can call spin density if you want. It's the last derivative that we have, and we have this relation between energy density and pressure. Little s is the derivative of pressure with respect to temperature. Like what? Not if you want it to be consistent with this. I think I know which term you're thinking about. You need derivatives there. You need derivatives there because if you want the second law to work, then it's actually going to be a term that drops from the equations of motion, and you need derivatives of that term in the stress tensor. If you add more terms here, the second law is just not going to work. Second law won't work. So if you want the second law to work, this is the only thing you can write down. I put all three. I'm sorry. Well, I'm assuming zero order in derivatives, so I don't have any gradients. I don't need anything else. I'm writing the most general thing I can that doesn't have any explicit gradients in it. So of course, if the system has some features. No, but it won't be. It won't be. Not in this theory. I need to add more things. It won't be because how can it be? If it's completely antisymmetric, you're going to get a u row. And then this is antisymmetric. This row has to be antisymmetric. So you're going to get this little row is antisymmetric. So the only way this can be fully antisymmetric is you have two u's here. You're going to get 0. This is the only thing that'll satisfy this. So I want to satisfy, I want to satisfy this, and this. No, this is so there are many spin. So if you want to do what you call a pseudo gauge, let's do a pseudo gauge. So S goes to S plus some phi, and T goes to T plus some grad phi. You see this? This can't appear in my theory because I didn't allow derivatives. This is part of what, so that's why you don't see all the terms that you like to see, because again, there are no explicit derivatives. In order to see these terms, I'm going to have to allow first order terms and derivatives. And we'll see them. Once I add them, you'll see them. So it's the variation of the action with respect to the field bind. Up to maybe some number that I don't remember. No, this is, the action is I don't need a specific action. All I needed to know is that this is satisfied. I don't need to know, I don't have an action. I'm saying that if you define the spin, I have a partition function, which is, or maybe say a generating function, which is going to be something like integral of P. I don't know if you can see this. And that's it. That's all I need. Now I need to know this. If I know this, I can extract from W I can extract from WS, and the claim is that this is the most general thing. Again, no explicit derivatives. Yeah. Yeah. But you get like pressure and absorption of these. I mean, you get terms that are orthogonal to mu. I have to see. I don't know. You have to show me. I have to. What can I say? Maybe we made a mistake, but this is what we got. You don't need this. This is a trick. You don't really need. You can do without this. I mean, I can look, but you can have extra terms which don't contain any derivatives. That I disagree. The question is whether your terms are just a frame transformation of this. That could be. You could shift things by frame transformation, but then you'll get derivatives. I don't see this. I can check, but I don't think you'll get anything. Let me just. No, but then otherwise it's a field redefinition. What else can it? Yeah. 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 No, but okay, this. Yes, yes, but you can if you want. Sure. No, but this. Okay, why? I don't know. I mean, you don't have to do it this way. I think you can shift the definition of mu, but then you're going to get some. You're not going to get your first law is probably going to be modified. Fine. Oh, well, I'm thinking, no, yeah, so in this case, it's kind of trivial, but you can imagine that you have conformal symmetry or parity, for example. Here, you can imagine you have an epsilon tensor, and that'll add more terms, so that's what I meant. I didn't put in conformal symmetry. I'm just saying compatible with whatever symmetry I have. So in this case, it's parity. Okay. Okay, so now let's look at the equations of motion. These are the equations of motion. And I'm looking at a particularly interesting set of the equations of motion. Because, well, you see sort of the problem here. The equations of motion themselves are not balanced. So on the left-hand side, we have a term that has an explicit derivative in it. And on the right-hand side, we don't have an explicit derivative in it. So the equation for the spin current naturally breaks our standard derivative expansion. Okay, so in a sense, if we really want to say that we're working in a derivative expansion, what we're doing is inconsistent in this sense. We have an equation which is supposed to be leading order, but it's really mixing different orders. Okay, so to resolve this, what we have to do is really say that the spin chemical potential is first order in derivatives. And once we do that, we have to again work through everything we did before. We assume local constitutive relations, derivative expansion, write down all terms that are compatible with the symmetries. Now that we didn't impose the third law yet, we have this extra term that I think you guys maybe wanted to see. And the next thing we do is impose the second law of thermodynamics, assuming the equations of motion are satisfied. Now, if the equations of motion are to be satisfied, we need to have this extra equation. So in order to really make sure that we're working consistently in a derivative expansion, we need to expand the stress tensor, the symmetric part of the stress tensor, the current, and the spin current to zero order in derivatives, and the antisymmetric part of the stress tensor to first order in derivatives. And that way we can get a consistent set of equations. Okay, so for that, we need to go back to first order in derivatives, write down all possible scalars, and it turns out that there are more than what we expected. And we do this analysis, write down everything, write all terms that are going to be compatible with the symmetries. So let me just ignore the current for a second to simplify my result. So we have all these coefficients. We remove terms that are equivalent under the equations of motion, and we impose the second law of thermodynamics, and this is what we get. Okay, so this is what we get if we work perturbatively in derivatives and we allow only terms that are, and we treat the spin chemical potential as first order in derivatives. So let me just explain what we're seeing here. This term here is a standard expression in zeroth order hydrodynamics. If it's conformal, then there's a particular relation between energy density and pressure. These terms here won't enter into the equations of motion, because these are what you're used to call, I think what you call pseudo gauge. They can be removed by a pseudo gauge. Okay, so the hydrodynamic constitutive relations also have this ambiguity, and it's reflected in hydrodynamics in this way. So we can add or subtract terms in a particular way, but notice that, as I said before, we're going to mix terms at different orders in derivatives when we do this transformation. Okay, and the last thing we get is a set of, is these first order terms in the antisymmetric part of the stress tensor, and these reduce to algebraic equations of motion for the spin chemical potential. And under the equations, under the using the other zeroth order equations of motion, this is just thermal vorticity. Okay, so what we've done here is we've reproduced thermal vorticity. This is again a zeroth order or first order, well, depending how you count, zeroth order constitutive relations or first order derivative expansion. Yeah. No, it can depend on temperature and chemical potential. Okay. So this is sort of an inviscid kind of analysis. What we really want to do is add some sort of viscosity. Okay, so for the stress tensor, it's fairly straightforward to do. What we get is some first order correction to the stress tensor. So we have a shear viscosity and a bulk viscosity. These are the standard terms that you're used to. And this term here is a partner of the other orange terms that you've seen before. It ensures that this term won't enter into the equations of motion. Yeah. Yeah. Perturbatively. You mean if I don't treat it perturbatively? I think at first order probably not. No, yeah, at second order you might, yes, but at first order you won't. Yes. Okay, so this is really the interesting part. So now there's a question of what sort of dissipative terms can we add to the spin current at first order and to the antisymmetric part of the second stress tensor at second order. Okay, so let me just ignore these terms that are that come from that don't enter the equations of motion. I'm interested only in terms that actually change the equations of motion. And what we need to do is just do the same thing, except we need to go to second order and derivatives, write down all possible second order terms, reduce the equations of motion, reduce the number of second order terms using the equations of motion, and we can use field redefinitions. I'm not going to show you the full result. I'm going to show it a little later because there's still some work to do that I want to highlight. But you can do this and you get the actual values. And here is what we get for the equations of motion for the spin chemical potential. Okay, so this term is a leading order term that we've seen before. And then there are many subleading terms. This is one of them. Okay, I want to focus on this one because it's a little confusing. If you think about this in a local rest frame, we have here a time derivative of the spin chemical potential. And you might think that this changes the equation from an algebraic one to a differential equation. Again, if we're thinking about this perturbatively, doesn't matter. This term is going to be a source to the expression there. And I want to emphasize this. What we need to do is we need to use the equations of motion. So we don't use only the equations of motion for the stress tensor and current. We also need the equation of motion for the spin current. The equation of motion for the spin current at leading order says that this is what the spin chemical potential looks like. So we can insert that here. Okay, and what we get is an expression of this type. So as long as we're working perturbatively in gradients, we can just replace the time derivative of the spin chemical potential with the time derivative of the thermal vorticity. Okay, so this is one thing we can do. But another thing we can do is we can just do a field redefinition. Okay, so we can take the spin chemical potential at 0th order, and if we want, we can shift it by a second order term. Okay, so here I shifted it by a second order term, but you can see what's going to happen. If I shift it by a second order term, then I can just get rid of everything that's not the leading term. Okay, so if I do this, I can just work in a frame where the second order term, all second order terms vanish. And in fact, all higher order terms vanish. This isn't the hydrostatic frame that you like. The hydrostatic frame will have this term, but in principle, I can go to any frame I want. And again, as long as I'm working perturbatively, everything should work out. Okay, so let me show you the end result. And I'm going to work with conformal hydrodynamics just because I can remove many terms this way so that I get a simple set of equations. So what I want is the constitutive relations for the stress tensor current and spin current. And I'm going to turn off all the background sources. So here is the stress tensor. It has a canonical part, which looks like this. So here is just the regular leading and first order terms in derivatives. This term here has to do with an anomaly. So I'm assuming that I have a U1 anomaly, and this is related to the chiral vortical effect. This is something that's known. So what you see in the canonical stress tensor is just the standard stress tensor in a particular frame. There's nothing new here. This is the antisymmetric part of the stress tensor. So what you're seeing here is the standard thermal vorticity term that we've seen before. So again, there's nothing new here. The tensor part is equal to the vorticity, and the vector part is equal to the acceleration under the equations of motion. Now, it turns out that if I have a chemical potential, then there are other terms that I can add to the antisymmetric part of the stress tensor that are consistent. Okay, so I can, for example, add these two terms to the antisymmetric part of the stress tensor. So these are one derivative terms. They're the same order as that term over there. We can't get rid of them with by using a field redefinition. So you see this is an epsilon tensor contracted with this derivative, and here we have same type of thing, but without um, an epsilon tensor. So this is going to modify. This is going to modify the leading order relation between spin chemical potential and thermal vorticity. The extra contribution is going to look like this. Of course, if this is small, or if sigma tilde E is 0, it's not going to contribute. Okay, so this comes from the standard term, and this comes from the correction. And then there's another term that we can write down, which again has to do with this parity violating epsilon tensor that we can add. This exists even if we don't have a chemical potential, again, as long as these coefficients are non-zero. Okay, so this is an extra parity violating contribution. Okay, so these are the terms we found, and of course there could be higher order derivatives, but we can also choose a frame where they're not there. So let's do that. And the other terms are terms that won't affect the equations of motion. So this, we've seen this term. It has a parity odd cousin, which is completely antisymmetric. And in addition, so these are zero order in derivatives, and there are four more terms that are first order in derivatives. Okay, so these are the extra terms we have, and those are the possible pseudo gauge transformations that we can carry out. Okay, there could be higher derivative terms to that, which we didn't compute. Okay, for the current, things are simple. This is just a regular current. This is a term that comes from the anomaly. I turned off, there could be a term that's proportional to the magnetic field. I turned off all the sources, so I didn't write it down. And there's the spin current, which is purely pseudo gauge. Phi is this term here. And yeah. Okay, so let me end here. This is our end result. Yeah, that's it. Thank you. Yes. It doesn't have to be totally antisymmetric. No. When you have a conformal symmetry with a spin current, if you have an antisymmetric part of the stress tensor, your constraints on conformal symmetry change. You have to, it's not just taking the, you can't make it traceless and it'll work. You have to work a little harder. This is invariant under Wild transformations. But you have to be a little more careful once you have an antisymmetric part of the stress tensor. I don't have it with me, but I can show you it in equations. Once you have, first of all, once you have conformal symmetry, once you have conformal symmetry, you have to ask yourself, how does the torsion get modified under conformal transfer, under Weil rescalings? This is a question you have to ask yourself, right? If you want to change your sources, if you have flat space and you're saying, I'm doing a shift of flat space, I'm changing it by some exponential of something, will torsion change? Yeah, yeah, yeah. Yeah, but you have to change the torsion too, maybe. You have to ask yourself what happens to the torsion tensor under Weil rescalings. And then there's some ambiguity that exists there because you have some freedom in choosing how torsion changes under Weil rescalings. If you take all that into account, I can show you this in equations. Yeah. What do you mean modified? So in non-relativistic hydro, I think the spin completely decouples from other things. So I think you're just going to get an extra U1 current that doesn't do anything. Well, yeah, that's a good question. So the point is that the way, so what you're going to get is that regular hydro still does whatever it does. So you're going to get, so the way we worked it out, you don't, once you have, I mean, you're going to get the standard hydrodynamic equations for the velocity and temperature, and the spin chemical potential is completely determined by those. That's what you're going to get. Yes, 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 yes. Otherwise you can worry. Yes. So there are some that maybe uh, that's right. This is a pseudo gauge transformation. It doesn't enter the equations of motion. How do you, I mean, it is what it is. Now, if you want to choose a pseudo gauge where everything is fully antisymmetric, then you're setting zeta 1 to 0. That's all you're doing. Whatever pseudo gauge you use in your microscopic theory to do whatever you're doing, it's just going to manifest itself in hydrodynamics this way. So if you manage to find some pseudo gauge where the spin current is fully antisymmetric, the only, assuming we did our computation properly, the only way it can enter is through, if we're looking only at the zero order terms, is through this. It means that zeta tilde 1 is going to be non-zero. Zeta 1 is 0. Okay. This is what you can find pseudo gauge where the spin density is 0 and the problem is solved. Well, if you do, but this is yeah. Okay. Yeah. But you have it here too. This is fully pseudo gauge, so you can do that. Sorry? Yeah. I hope I copied correctly, but I think it's this one. Yeah. Yeah. What do you mean assume spin is conserved? But it's not. It's not. No, but it's not. It cannot be. What I'm saying is that it cannot be. It cannot be. Okay, it depends what. No, it means that I need to do a pseudo gauge transformation that'll get rid of some terms. And then I'd need gradients. Yes. It can't be. Because it's variation with respect to u mu. So it's always orthogonal to u mu. Because u squares to 1. So you do a variation with respect to u, it has to be orthogonal to u. So p is orthogonal to u. So you're saying that it's impossible without gradients to have ideal spin hydrodynamics with a significant. Let me say maybe, let me say this. Right, so this thing with the pseudo gauge, let's do the following. So you have you have, let's suppose you don't have any charge. So you have this equation, and then you have this equation. Right? So this is the generic thing that you'll get. You have to define what these objects mean. Okay. Now what you can do is you can say, okay, now what does this really mean? What this equation says is that you can take your equations of motion and you can massage them so that they look like a divergence of a stress tensor. Right? So what you really have here is this thing. Equation of motion. This is the equation of motion. If the equations of motion are satisfied, this is what Noether theorem tells us. Noether theorem tells us that if the equations of motion are satisfied, stress tensor is conserved. So another way of thinking about this is to say that the divergence of the stress tensor can be written as some equations of motion and maybe their derivatives. Okay, same thing here. Okay. Now, what you can do is you can do this thing and simultaneously call this T prime and call this S prime. Or minus phi, I'm not sure, but it doesn't matter. Okay, and what you'll find once you do this is, as you know, it's going to be this thing. Okay, so it's really not going to make any difference. And now what you can say is, well, fine, let's just choose, I don't know what you want to choose now. You want to choose T prime to be 0? What do you want to choose? You want the antisymmetric part of T mu nu to be 0. So you need to find some phi which will make the antisymmetric part of T mu nu 0. So now, to do that, you have to add a gradient of something. Also, sorry, what? No, no. No, but look. No, but that can't, again, that can't exist. This, let me say it this way. Let's continue. Let's just continue this. If you want the antisymmetric part of the stress tensor to be 0, you need this term here to be 0, right? So in order to do that, the only way you can do that using phi, your local variable is phi. Okay, so you need some local phi that'll make this thing vanish. Okay, so now you have to ask how to either you somehow find some gradient of phi which will make only this vanish, but that means that phi won't necessarily be local. You have something here that's local in the fields, and you have something here. Okay. I would say not only, it's only one. It's only one. You don't have any, in hydro, in terms of hydro variables, you don't have any more because you have to have a derivative and you don't allow derivatives. So you don't have any. Yes. In terms of hydro variables, in terms of, yeah, you can see it. I mean, there's no, you see, once you have this, you're done. What do you mean? Is this? No, I. Yeah, but you do, yeah. But let me also point out that what in principle, what you could do now is you have this, and now you can just expand the pressure. You say, okay, I'm going to keep this, but I'm going to treat these things as higher order in derivatives. So you expand the pressure, it has a leading term, which is 0 order in derivatives, and then it goes like m squared, so that's going to be second order in derivatives. So you can just expand this whole thing in a derivative expansion, and then do whatever frame transformation you want. Yes, but it's equivalent. Yes, but now you project it orthogonal to the velocity. Okay. No, what I meant was that the equations we get are equivalent to saying that the spin potential is equal to the thermal vorticity. This is what I meant. It's equivalent. Okay. Yeah, okay, point taken. Yeah. Yeah, it's this term. I know what it is. It's this one or the one before? This one? That's right. Not only that, I can also say that this term will be there in the fluid frame that you like. In the hydrostatic frame, which I think is equivalent, I mean, we can check, I'm pretty sure it's equivalent to what you call local thermodynamic equilibrium, you will get this term. And this term, like you mentioned earlier, it's the time derivative of the spin chemical potential, so it gives you some sort of relaxation. So if you use the hydrostatic frame and not the frame where everything vanishes, you get this term. But again, you want to get interested. So first of all, you have to say why you want this term, and you might have some physical idea, or it's natural to have this term. And then you have to treat it non-perturbatively for whatever reason in order to get interesting physics. Okay. And the other one? I see. Okay. Because I know that, I don't know how it is in the quark gluon plasma. I mean, I'm guessing that chemical potential or gradients of chemical potential are probably small, but the other term, you know, if it's order 1. So unless it's okay, but okay. What? What is U? U mu? Yeah. Yeah. Okay. This is yeah. 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 No, no, it's A mu is order 0 in derivatives. So derivative of lambda, derivative of, if I take A, if I do a gauge transformation of A, I don't know what you want to call it, theta, right? Then it means that theta is order -1 in derivatives. Hmm? Well, I don't have any extra, I don't have, the pseudo gauge is not a transformation of the chemical potential. Pseudo gauge means that it's this. It's this. So these phi's are, you know, when you change the stress tensor, you change it in terms of the fields that are available to you. So in hydrodynamics, the fields that are available to me are these. This is a solution. This is a solution to the equations of motion. This is a solution to the equations of motion in equilibrium. Wait. No, no, no. There are two different things here. When you say a solution, what do we mean by a solution? If we have the hydrodynamic equations, right? If we have hydrodynamic equations, then what we're saying is the following. I have this, and this depends on, let's say, temperature and chemical potential. When I say and it depends implicitly, if you want, it depends implicitly on the metric. So when we solve this, it means that we have the temperature completely determined by the metric, and we have the chemical potential completely determined by the metric. Completely determined. No, 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 because this relation is not of the type you're saying. This is not the same thing. I need a solution. What happens in hydrostatics is that you have a killing vector. The killing vector, you determine it from the metric. It's not. You have to interpret the killing vector as a velocity. It's an extra step you're taking. The velocity field as a solution to the equations of motion is a solution, and you find that in equilibrium, the velocity field is going to be your killing vector, normalized. And what you find is that the thermal vorticity is going to be whatever, this gradient be antisymmetric. As a solution, this is a solution. So I have dynamical variables are functions of sources. Killing vector is a property, is a source. So here too, the mu over t is a function. This isn't really right. If you really want to think of this as it has to be something like that. But it's all a function of sources. You're already solving the equations of motion. So, but this isn't a solution. This is the constitutive relations. What you can do is you can say, well, I know that once I go to equilibrium and I solve the equations of motion that follow from these constitutive relations, I will get this. That imposes constraints on the structure of the constitutive relations, which is exactly what local equilibrium, or what I call hydrostatic, does. Okay, but that's what it is. You have here some, you know that after you solve the equations of motion, then your hydrodynamic variables will be functions of something that's not hydrodynamic, some sources, particular velocity field or whatever. So that is going to constrain this. Yeah. Yes. Well, yes, because to impose the second law, you need, what you say is that the second law is valid once the equations of motion are satisfied. So I need something. I need to start with, yeah, so the second law constrains the equations of motion. Sorry, pardon?